Flying has been one of humanity's most impressive feats, from the Wright brothers' humble beginnings to the modern marvels of aerospace engineering. The principles that govern flight remain fundamentally unchanged. At the heart of flight are four critical forces: lift, thrust, drag, and weight. Each force plays a pivotal role, and their interaction dictates whether an aircraft can take off, stay airborne, or safely land. Let's dive deep into each of these forces to understand their science, how they're controlled, and how engineers tweak them to push the limits of aviation. Lift. Lift is the upward force that opposes the weight of the aircraft, allowing it to rise into the air. This force is primarily generated by the wings, which are specifically designed to manipulate airflow. To understand lift, we must examine the angle of attack, airfoil design, and the physics principles underneath it. An airfoil is the cross-sectional shape of a wing, typically featuring a leading edge, trailing edge, chord line, and a camber line. The chord line is the straight line connecting the leading and trailing edges, while the camber line curves along the wing, showing its shape. Wings are designed with a curved top and a flatter bottom to create differences in airflow speeds above and below the wing. As air travels over the curved top of the wing, it speeds up, creating a low pressure environment. Below the wing, where the air moves slowly, a high pressure environment is formed. This pressure difference generates lift according to Bernoulli's principle, which states that an increase in the speed of a fluid, air, results in a decrease in pressure. At the same time, Newton's third law contributes air deflected downwards by the wing generates an equal and opposite upward force. The angle of attack is the angle between the wing's chord line and the oncoming airflow, which also significantly affects lift. A higher angle of attack increases lift to a point, but exceeding the critical angle causes the airflow to separate from the wing's surface, leading to a stall. Stalling occurs when the smooth airflow over the wing is disrupted, drastically reducing lift and potentially leading to a loss of control. This highlights the importance of balancing the aircraft's weight and carefully managing the flight parameters. Lift is interconnected with drag, particularly induced drag, which is a byproduct of creating lift. This drag results from vortices forming at the wing tips due to pressure differences, reducing efficiency. To counter this, modern aircraft are equipped with winglets or other design features to minimize these vortices. Flaps located near the trailing edge of the wing also play a crucial role during takeoff and landing. Extending the flaps increase the wing's surface area and curvature, allowing more lift at lower speeds. However, this also increases drag, which must be managed. The wing's design, including its aspect ratio, also influences how efficiently lift is generated. In gliding, lift is optimized by maintaining a low waist and an efficient wingspan. The ratio of lift to drag, called glide ratio, determines how far an aircraft can travel horizontally for every unit of altitude lost. Pilots and engineers work together to adjust the aircraft's center of gravity and ensure the optimal wing loading for longer, controlled descents. thrust. Thrust propels the aircraft forward and counteracts drag. It is generated by engines which can range from jet engines to propellers. In jet engines, thrust is produced by rapidly expelling exhaust gases. This is another application of Newton's third law. As gases are forced out at high speed, the engine pushes the aircraft forward, which with an equal and opposite reaction. Thrust must be sufficient to overcome both drag and weight for the aircraft to accelerate and maintain flight. Engineers designed engines with a balance between power and efficiency. For instance, turbofan engines on commercial flights are optimized for high thrust and fuel efficiency at cruising speeds, while military jets prioritize raw power and speed. The amount of thrust required depends on various factors, including the aircraft's weight, altitude, and air density. At higher altitudes, where the air is less dense, engines must work harder to produce sufficient thrust. Engineers often consider the thrust-to-weight ratio, a critical metric for determining an aircraft's performance and capabilities. A high thrust-to-weight ratio allows for faster acceleration and steeper climbs, which is especially important for fighter jets. Thrust also interacts with lift, as the forward motion generated by thrust increasing the airflow over the wings, enhancing lift. This interplay is crucial during takeoff, where pilots need to achieve sufficient speed to generate the required lift. During cruise, thrust balances the drag and to maintain a steady speed. Drag is the opposing force to an aircraft's forward motion through the air and is intricately connected to the airfoil's design and lift it generates. It primarily arises from two main types: parasite drag and induced drag. Parasite drag results from the overall shape of the aircraft disrupting the smooth airflow. Skin friction drag occurs as air molecules cling to the aircraft's surface, particularly the wing skin. Interference drag forms where different components of the aircraft meet, such as the wing and fuselage junction. Induced drag, however, is directly tied to lift. As the wing generates lift, the pressure difference between the upper and lower surfaces of the airfoil creates vortices at the wingtips. These vortices generate a spiraling airflow, increasing its resistance and reducing efficiency. The stronger the lift force, the greater induced drag, which making it a crucial consideration in wing design. The design of the airfoil includes its chord line, camber line, leading edge, and trailing edge, plays a pivotal role in managing drag while maximizing lift. A well-designed example of this would be a more pronounced camber curvature, enhancing lift by increasing the pressure difference across the wing. However, it also increases drag, especially at higher angles of attack, as airflow begins to separate from the wing's surface. The aspect ratio affects drag as well. Higher aspect ratios reduce induced drag, making gliders with long, narrow wings more efficient during flight. The interaction between lift and drag is represented by the lift-to-drag ratio. Aircraft with high lift-to-drag ratio, such as gliders, are more aerodynamically efficient as they generate significantly lift for minimal drag. Engineers aim to optimize this ratio by carefully shaping the airfoil and using features such as winglets to mitigate induced drag. The relationship between lift and drag also ties to the fundamentals of physics principles. According to Bernoulli's principle, the faster airflow curved upper surface of the airfoil creates a low pressure zone, while the slower airflow beneath the wing creates a high pressure zone. This pressure difference generates lift, but also contributes in reduced drag, as the wingtip vortices dissipate energy, as we already told. Newton's third law plays a role too. The downward deflection of air by the wings at the angle of attack results in an equal and opposite upward force, generating lift. However, this deflection also increases the forces by disrupting the surrounding airflow. Weight is the downward force due to gravity, calculated as the mass of the aircraft multiplied by the gravitational acceleration, 9.8 meters per second. It acts through the center of gravity, which must be carefully monitored to maintain stability. Weight directly affects lift and thrust requirements. A heavier aircraft demands more lift, which in turn requires a greater thrust. Managing weight involves optimizing materials, fuel loads, and even passenger distributions to ensure the aircraft remains efficient and controllable. Aircrafts are constructed with using lightweight materials such as aluminum alloys, composites, and titanium to reduce weight without sacrificing strength. Fuel efficiency is another critical factor, as reducing consumption minimizes both weight and operational costs. Engineers also consider the payload capacity to balance economic and aerodynamic efficiency. In steady flight, all aircraft lift must be equal to maintain altitude. Thrust must equal drag to maintain a constant speed, and any imbalance results in changes in motion. For example, during takeoff, thrust exceeds drag and lift exceeds weight, allowing the aircraft to ascend. During landing, thrust and lift enables a controlled descent. Understanding these forces is essential for designing, piloting, and advanced aircraft technologies. Each principle, from Bernoulli's airflow to Newton's action-reaction, forms the foundation of modern flight, ensures safe and efficient journeys for passengers and cargo.